In this video, we're going to look at using integration to find the area bounded by a curve and the x-axis. When we first looked at integration, it was introduced as the reverse of differentiation. We view this as a very mechanical process. We raise by a power, we divide by the new power, and we add a constant of integration. We call that an indefinite integral. In this video, we're going to look at finding the area bounded by a curve and the x-axis using a definite integral. And we can say that the area is given as the integral from a to b, where a and b are two x-coordinates of y dx. Now, this is an elongated s, and in Latin it stands for the sum. So it comes as no surprise that we could actually use now the integral, and this is a definite integral, as I've got these limits, to find the area bounded by a curve and the x-axis. Rather than just plug in numbers in, what I want to do is see how that works. So let's take now some function of x. So y is a function of x. What we've got here now are the limits a and b. So we're interested in the area trapped under the curve between x is equal to a and x is equal to b. What we've got here is a rectangle. Now, if I have loads of these rectangles here, we can approximate an area trapped under the curve between these 2 points. The rectangle has width delta x. Delta x is just some small increase in the x-coordinate. We've got a height of y. Now, as delta x tends to 0, i.e. it becomes very, very small, and that becomes infinitesimally small, we're going to end up finding the area. So, for example, if this now was 1 unit, if I made that half a unit, if I made that 1/10 of a unit, the more of these we have, the better the approximation. So, if we look now at the area of each of these rectangles, and let's just call that area now delta A. So I'm going to say that the area of each of these rectangles is going to be delta A, and that's going to be given as now delta x multiplied by y, or y multiplied by delta x. So I could get an approximate area, and the approximate area would simply now be the sum, and I'm using the sigma notation, from x is equal to a to x is equal to b, now of this delta A right here, which is going to be y, and then we're going to have delta x. So you can see if I now put one up, and when I'm saying that this is going to be infinitesimally small, if I think about how small this width I can get it, once I think I've got it really small, I can get it even smaller. So we might have a rectangle that's of width now, this thickness. I could even now divide that by 100, by 1,000, and that's what we're talking about when we say now the limit of delta x tending to 0. Now when that happens, what we end up with is the area equal to, and we say as the limit of delta x tends to 0, we will have the sum from x is equal to a to x is equal to b, now of y delta x, and this will give us the area. And that is essentially where we're going to get back to this. Now, this one here looks quite daunting. We've seen this one, but essentially it's the same thing. All we would have to do is rearrange and integrate, and we would get exactly the same expression. So what we can say then is the following. We can say now that the area is given as the limit, and this is as delta x tends to 0, and we've got now the sum from x is equal to a to x is equal to b of y dx will be equal now to the integral of y, and this is going to be delta x here. We've got y dx, and this is going to be from a to b. So that's what we can say. So as delta x tends to 0, we can actually use the integral to find the area, and this now gives us the area bounded by a curve and the x-axis. We can of course look at the area bounded by the curve and the y-axis, and out of interest that would give us now the area would be equal to the integral from a to b, and instead of now y dx it would be x dy. So it shows now that all we have to do is essentially integrate and evaluate, and we'll look at how to evaluate these limits, and this will give us now an area bounded by the curve. So once we're given some function of x and we're given now some x coordinates to find the area between, we simply go ahead and go back to that mechanical process depending on what kind of function we've got. Initially we'll start with basic polynomials. We'll be raising by a power, dividing by the new power, and then we evaluate the limits. As your work goes on, you will look at some more complicated functions. So you might look now at the natural log of x. You might look at some trig function. But let's go ahead and have a little go at this. Now, at this moment in time, you're looking at this thinking, well, I'm not really sure that it's going to work. Let's actually show it's going to work. Let's choose something that we can deal with. What I'm going to do is just draw a graph, and we're going to now use integration to find the area trapped under the curve between two limits. And I'm just going to choose some limits. So let's now draw this line right here. And I'm going to say that this line is going to be, now let's say that this is going to be y is equal to 2x. Okay? So y is equal to 2x, and I'll state now that this is going to be 0, and let's say that this is going to be 4. Now if this is 4, then this coordinate just here is going to be 4, 8. If y is equal to 2x, that's what we've got. So what I want then is the area trapped now between this line and the x-axis. Generally we've got a curve, but in this case obviously it's a straight line. So what I'm going to do is find this area right here. So what I can say is the following. I can say now that the area will be equal to the integral from 0 to 4. So I'm taking now a to be 0, b to be 4, and we're going to say that this will be the integral of 2x, and we're integrating with respect to x. Now, when you're integrating, you can take the constant, and the constant in this case is 2, the other side of the integral sign. If you're not confident with that to begin with, it's perfectly fine. Now in this particular case it's of no real benefit for me to do that, as we'll see, but it's just something in the future to cut down the amount of number crunching you're doing. Often pulling a fraction out means that your work becomes easier. So let's go ahead and integrate this. So what we've got then is a will be equal to, now, and we raise by a power and divide by the new power. So what we'd end up having is x squared. Now that is the integral of 2x. I'm going to evaluate between the limits now of 0 and 4. Now when we're evaluating, we can say now that the area will be equal to, now all we're doing is putting 4 in here, so we're going to get now 4 squared, and then we subtract away now 0 squared. So when we evaluate limits, we evaluate now the larger value here and then subtract away the smaller one. So we can see that the area is going to be from here 16, and that would be now units squared. So all I've done is evaluated. If I have that this was 3 and this was 1, we'd do 3 squared minus 1 squared. Now it's telling me that the area trapped under this line and the x-axis is 16 units. Is that true? Well, let's just look at it. All it is a triangle. Triangle has got a base of 4. It's got now a height of 8. So if we wanted the area of a triangle, it's 1/2 multiplied by the base multiplied by the height, and 1/2 of 32. The area is going to be 16. So if you were unsure of whether it worked, here is an example. That certainly isn't a proof, but it gives you some reassurance that this is going to work. Now in the video we're going to look at 3 different scenarios. We're going to look at the basic integral between two limits of a straightforward function, and we'll start with y is equal to x squared. We will then look at some other scenarios. In later videos I will do some more challenging problems, but for now we will look at a couple of scenarios that you might come up against. So let's say we were asked to find now the area bounded by the curve y is equal to x squared, the x-axis, and the lines x is equal to 1 and x is equal to 4. So the wording of these questions is often a little strange, but we'll get used to it and we'll work with it. So what we're going to do is have the curve, and we'll have the curve y is equal to x squared, which will look something give or take like so. So y is equal to x squared. Now I'm going to have an x coordinate just here of 1. I'm going to have an x coordinate just here of, let's say that this is going to be 4. So what I'm looking for now is the area bounded by the curve and now the x-axis, which is going to be this point right here. Okay, and it'll be there and it'll be there. That's just a rough diagram. So let's just shave this. So what we're after now is this area. So I want to find all of that under there. So what I'm going to do is write now that this is y is equal to x squared. So what we're looking for, we can say that the area will be equal to the integral now from 1 to 4 of x squared. And remember, we're integrating with respect to x. So I can say now that the area, all I'm going to do is integrate this. So the integral now of x squared with respect to x is going to be 1/3 x cubed. So I've raised by a power, I've divided by the new power. This is a definite integral. If we've got a definite integral, we don't need the constant of integration. The constant of integration just gives us a family of solutions. So we might have, for example, 1/3 x cubed plus c, where c is 1. And all you've got is just a range of different curves translated up and down the y-axis. We don't do that with a definite integral. That's just reserved for now the indefinite integral, or if you like, the antiderivative, which is a less well used term. Right, let's go ahead and do this then. Let's do 4 and 1. So what we're going to get, and at this stage I'm just going to leave the 1/3 outside. So I'm going to evaluate 4. Now, when you come to exams, do have a look at the mark scheme of any exam that you're sitting. I'm doing this quite informally at the moment, but often you need to show full working. So if we had some polynomial, say it was x squared plus 2x plus 3, and we integrated, we'd have to show that we were subbing 4 in each time. What I'm going to do though is just go ahead and do this. So what we've got then is 4 to the power of 3 minus 1 to the power of 3. And as stated, this is very simplistic. In later videos, we will look at the correct way to proceed with this. So what we've got then is the area will be equal to 1/3. 1/3 is just a constant. That's going to be now 64. 3 cubed is 64 minus 1. So the area is going to be equal to 63 over 3, which looks to be 21. So we've got now 21, and that's square units. You won't be expected now to give any units on this. It might say give your answers in square units, but essentially that's what we end up with. So this is the first scenario. Nice straightforward integral between two given limits, and it's a nice, nothing to concern ourselves with, and we have this scenario. Okay, let's look at something else. Let's say now we wanted the integral, and we've got the curve y is equal to x cubed. Okay, so let's take x cubed, and we want to find the area now bounded by the curve, the lines, and we'll write the lines here. X is equal to -2, and now x is equal to +2. So I want the area trapped under the curve, trapped between now the curve and the x-axis. So let's go ahead and do this. So we can say now that the area is going to be equal to the integral from -2 to +2 of x cubed dx. So let's go ahead and integrate. So area is going to be 1/4, we raise by a power, divide by the new power, 1/4 x to the 4th. Now I'm interested in this between -2 and +2. So let's do this right now. So what I'm going to have then, I'm going to take the 1/4 out, that is a constant, 2 to the power of 4, so 2 to the power of 4 minus -2 to the power of 4. So all we're doing is subtracting one area from the other. So what we've got then is 1/4, and that's going to be 16 minus 16. And that tells me that my area is going to be 0. Now, quite clearly, there's some area between that curve. So my first question is, what have I done wrong? And the answer is, I haven't sketched this. Now, if I went ahead and sketched this beforehand, and this is something I suggest you do a fair bit, is get some understanding of what's going on. If we think of the curve now, y is equal to x cubed, we've got now this coming up here, and then we've got this coming up here. So that is going to do something like that. Now I've just gone ahead and integrated here between -2 and +2. I've got a positive area just here of 16, and then my integral has given me -16. When I've added them together, I've ended up now with these two areas cancelling out. Quite clearly there's area. So what I should have done now is said that the area was equal now to the integral of x cubed between, now let's take it from this point 0 to 2, so 0 to 2 plus now, and we say the modulus. This is the absolute value. We make this value now positive, and this is going to be from -2 to 0 now of x cubed. And again, we should have a dx just there, but that is essentially what we're doing. We're finding now the negative area, and we're turning that positive. This just means the absolute value, so the numeric value. So we can see that the area is actually now 32 units rather than 0. And we need to be very careful with this. So when we're now passing through the x-axis, cutting the x-axis, we consider how that's going to work and we split that area up. So just a nice little sketch beforehand and you can work that out. Let's have a go at one of those then. So let's just choose a function. Let's say we've got some function. Let's say y is equal to, let's go for x, and then we'll have x minus 1, and then we'll have now x, let's go for x minus 3. And we might be asked to find the area enclosed between the curve and this x-axis, or the x-axis and this curve, I should say. So let's go ahead and actually do a sketch. So what we've got then is a cubic function. So if we set y equal to 0, we're going to have a point of intersection now, and we're going to have 1 just here, and that's going to be 0. We're going to have 1 at 1, and we're going to have the other one at 3. So cubic function is going to come through the third quadrant. It will turn round, it will come down, will come back round, and will now disappear. It's a positive cubic. We will disappear now out of the first quadrant. We've got this point 0, so if we set now this to be 0, so if y was equal to 0, x is 0, 1 is 0, so x is equal to 1, or x is equal to 3. So we've got 1, and then we've got this point 3. Now we can see quite clearly, if I take the integral from 0 to 3, I'm not going to get the correct answer. What I want to do is consider this now as two areas. So I'm going to consider the absolute value of this one. So I'm going to consider this area right here, and if you want, you can call this area A, and add it to the modulus of area B. Okay, so if you wanted to do that, you can call this A and B. So if we now look at A, what we're going to have is the following. A is going to now be, for the area, we will have the integral of this right here. Now what I'm going to do is expand this out. So if I expand that out, what am I going to get? I'm going to get, in this part right here, x squared minus 4x plus 3. So if I just write it out now, I'm going to have the integral, let's just work this out, x cubed. And all we do with the techniques that we got is just expand this out. So what we're going to have, x cubed minus 4x squared, and then we're going to have plus 3x. So plus 3x. All I'm doing is just mentally just expanding this so we can now sum this. So what we're going to have then is the integral. Now I'm going to have this from 0 to 1. That will give me the positive. So this right here, and let's just put this on, this now is going to be A. So let's say that this is going to be A, and that isn't a very good A, so we'll put it here. And this one, let's put that as B, that's going to be B. So what I want then is the integral from 0 to 1. That will give me a positive value. Now for B, I'm just going to write B. What we've got then is the area, and we're going to take the modulus. So we're going to take the modulus, the absolute value now of the integral from 1 to 3, now of x cubed minus 4x squared plus 3x, and we're integrating this with respect to x. So whatever this value is, I'm going to end up making positive. So let's just go ahead and find the integral. So for now A, we can say that the area is going to be, and I'm going to integrate this, so raised by a power divided by the new power, 1 over 4 x to the fourth. As stated, we're dealing with these polynomials at the moment. Later on you'll go on to some more interesting work with other functions, but for now we're just using exactly the same techniques as we've done before. Raised by a power divided by the new power, so that's going to be minus 4/3, so minus 4/3 x cubed, and then we can have plus 3 over 2 x squared. So that now is our integral. So on the first one, what we're looking at then is the following. We're looking at the integral on here from 0 to 1, and on here the modulus of the integral from 1 to 3. And you'll notice that we're going to be evaluating the 1 twice, so we can simply use the values again. So let's do that now for, and in the exam you would show that you're doing this. So for now A, let's go ahead and do that. So let's put this is going to be 1 and 0. Now what you would show is the following. You'd show that the area is going to be 1 over 4 lots of 1, and this is slightly tedious, but you may be required to show it in an exam, plus 3 over 2 lots of 1. And then what we do is subtract away from that, and I'm just going to put 0 plus 0 plus 0. So 0 plus 0 plus 0, as if I evaluate 0 through here. So what's that going to give us? The area is going to be equal to 1 over 4 minus 4 over 3 plus 3 over 2. And I'm just going to put that through a calculator. I'm being a bit lazy here, I suppose I could switch all of those into 12s. But don't now make an error just to find this. Okay, let's get the calculator. So what have we got? We got 0.25, then we've got minus 4/3. So we've got minus 4/3, and then we've got plus 1.5. So I apologise for I'm being a little lazy here. 5/12. So that's the area right here. So this area is going to be 5/12. Okay, so 5/12, and that's going to be units squared. Now, here, of course, I've just got now subtracting away 0. Clearly, if that wasn't the case, I'd then have to consider what I've got there. So what I can do now, this is for A. So I've now looked at the area trapped now between the curve and the x-axis between 0 and 1. I've now got to consider B. So the area will be now the modulus, and what we're going to have is the following. So we're going to have 1/4 x to the 4th minus 4/3 x cubed plus 3/2 x squared, and I'm interested in this now between 1 and 3. So let's go ahead and do that. So let's get to a value. So we can say now that the area, initially I'm going to get a negative, and I'm just going to put this in as I go. So that's going to be 81/4, so just subbing in 3 here, 81/4 minus, and then that's going to be, what's that going to be, 27, so that'll be minus 36. As stated, I'm being a touch lazy here, and then what are we going to get? Plus 27/2. And then what we'll do is subtract away, and remember I've already evaluated 1, and that gave me now the 5/12. So I'm just going to put that in. In the exam, you'd want to show this, so you'd want to put down 1/4 minus 4/3 plus 3/2. Okay, so let's go ahead and put this through a calculator and find this value. So at the end, I'm just going to now subtract away my answer. So what I've got then is 81/4, and I'm hoping my math stacks up here. If it doesn't, I apologise, and hopefully you can see exactly how I'm doing this. Minus 36 plus now 27/2, and then we're going to subtract away from this now the answer. So that's that part right there. I've just evaluated that. Now this is already the answer that I've got in the calculator, and that will now give us minus 8/3. So we can say then that this is going to be minus 8/3. Therefore we need the modulus. The modulus of minus 8/3 is 8/3. It's just the absolute value. So all I'm going to do is put this now that this is going to be 8/3. So this area right now is 8/3. So I just need to add the two together. So 8/3, if I switch it up into 12s, we just simply multiply it by 4, so 32/4. So we can say the total combined area is just the sum of these two, which is going to give me, so that should be 32/12, shouldn't it? I've managed, yeah, I think you can see what I've done there. Okay, so it's going to be the sum now of those two. So the sum now is going to be 37/12, and that would be units squared. So what we've done is considered two distinct areas. We've made the one under the curve now positive. So that's a nice example, okay? And it's something that you may do. So my suggestion is, once you're given a function, do sketch it to see what you're dealing with, as it's really quite important to do that. You might have some, for example, you might have a quadratic function. Let's do a quadratic function. Let's say we've got now a minimum point down here. Let's say we've got some minimum point, and our quadratic looks something, give or take, like so. Now we might have this point, and you might be asked to find, so let's say that this point right here is going to be 4. You might be asked to find the area now from here, and that might be, let's say that's 2. You might be asked to find the integral from now 2 to 5, and you can see that we got some of the curve in that interval right there. Some of the curve is going to be below, and then some of the curve is going to be above. So just be careful, and graph sketching is really going to help you out here. So there we go, nice example of finding now these two areas and adding them together. So there's two scenarios. First scenario, straightforward integral between two limits of a curve that's above the x-axis. This one we got half above, well, a portion above and a portion below. Now we might be given another example, and the example we might be given, let's have a quadratic. Say we've got y is equal to, let's go for x squared minus 3x plus 4, and we might now have a line. Sometimes it'll be a curve and a curve, less likely, so more likely a curve and a line. And we might be asked to find the area bounded now between these two. So let's draw a quick sketch. Let's have some form of idea. So this quadratic, what are we going to have? We're going to have something that looks, and this really will be a rough sketch. We'll have something that looks like this, okay? And it'll do something like that. Now if we have this line, let's draw a line. Let's say we've got this line and this line does something like that. I don't know how accurate or inaccurate that is, as it's just a sketch. Now what we want, and let's say we wanted this area right here. So we wanted the area now trapped between the line and the curve. What we're going to do is look at two particular approaches with this. So let's now take some values. Let's say that we wanted this now between the 2 points of intersection. So what we need to do is find those points of intersection. So let's go ahead and do that. Let's say now that we wanted this area. So the first thing that we need to do is find these points of intersection. So if we consider that y is equal to this and y is equal to that, then those two things are going to be equal. So x squared minus 3x plus 4 will be equal to x plus 1. So subtracting x and subtracting a 1 from both sides, that's going to leave me now x squared minus 4x plus 3 is equal to 0. That'll factor x minus 1, then x minus 3, and that will be equal to 0. So x will be equal to 1, and then x will be equal to 3. So we can see that this x-coordinate right here is going to now be 1. This x-coordinate right here is going to be 3. We have at this stage two choices, and I'm going to go for both approaches. The first one is that we find the area trapped under a curve, and we also find the area of a trapezium. Now if we consider that this is 1, then this point right here, the y coordinate, is going to be 1 plus 1. So this is going to have the coordinates just here, 1, 2. This one is going to be 3. 3 plus 1 is 4, so we've got 3, 4. Now what I could do at this stage is draw a trapezium. Now if I think about the area of this trapezium, what I've got is the following. It's going to look something like this. So I've got now the two parallel sides. The two parallel sides are here. So I've got now that this point is going to be 1 and this point is going to be 3. Therefore this is going to have a distance of 2. And all I'm looking at here is this. I'm just simply now drawing this to the side. So we've got now this trapezium. So this is 2. This one is going to be 4. And then this one is going to be 2. So the area of the trapezium is going to be 2 plus 4 divided now by 2 multiplied by the perpendicular height, which is going to be 2. So we can see from here that the area of this one is going to be 6. So that is 6. What I'm now going to do is find the area now trapped under the curve. And the area trapped under the curve between these two limits can be evaluated. We've seen that. So what we'll do is look for this area right here. Now, if I wanted the white shaded area, I'd simply go ahead and subtract the area trapped under the curve from this bit, and that would give me now this small sliver. So let's go and do that. Let's go ahead and do that. So what we can say, the area now is going to be equal to the integral from 1 to 3 of my curve. My curve is x squared minus 3x plus 4. So all we're going to do is integrate this. We're integrating with respect to x. So now we can evaluate. So we've got an area, and that's going to be 1/3 x cubed, raised by a power divided by a new power, minus 3 over 2 x squared plus 4x, and we're evaluating this now between 1 and 3. So let's go ahead and just put this in. So what we're going to have then is the following. The area is going to be equal now to, and I'm going to do this fairly quickly. So that's going to be 27 over 3 is 9. That's going to be now 27 over 2, so minus 27 over 2. Again, in the exam, show that you're subbing this in, plus now 12. From that, we're going to subtract 1/3 minus 3 over 2 plus 4. So all I've done here is just evaluated 3 and 1. I've taken the higher limit and subtracted away the lower limit. All I've done is put those in. So let's find that in a calculator. So what we've got then is the following. We've got 9 plus the 12. I'm just doing this in a slightly different order. Minus 27 over 2. And then we are going to subtract away from that. We've got now 1/3. And again, I'm hoping that my arithmetic stacks up. If it doesn't, hopefully you'll at least get in the, because I'm doing this as I go rather than pre-doing them. Hopefully you'll get some understanding. So what's that give us? 14 over 3. Okay, so 14 over 3. So if we look, the area trapped under the curve now is 14 over 3, and that's this point right here. So this part is going to be 14 over 3. So what I need to do is take this away from the 6, because I want the area now trapped here. So I know that I've got the area of 6, so all we're going to do then is the area of the trapezium minus the area trapped under the curve, okay? So if we look at that now, that will give us this sliver right here. So it's going to be 6, which I'm going to write as 18 over 3 minus 14 over 3, and that's going to give me now 4 over 3, and that will be units squared. So we found the area trapped between them. Okay, now, we saw before that integration was a tool for summation. Now, it would be it'd be pretty cool if we could simply think of a nicer way of doing this. And a nicer way is to look and say, well, actually, the curve is below the line in now this point right here, this interval from 1 to 3. It's now below the line. So surely I can just take the curve away from the line and integrate, because it's going to find now the difference of the sums. So what we could do instead is the following. What we can actually do is say, well, the line is above the curve. Now, if it was the other way around, if the curve was above the line, we would take the line from the curve. What I'm going to say then is the area, and I'll write it just here, it's going to be the integral from the points of intersection that we found with now the simultaneous equations. It's going to be x plus 1 minus now the curve. So all we're going to do is subtract that away and integrate. So this is what I'm going to do. I'm going to take this away and I'm going to integrate. Now, if we look at this, and let's get me some space. In fact, I'll write it just here and then I'll evaluate it. The area is going to be now the integral from 1 to 3. So we can have minus x squared. What else are we going to have? We're going to have now plus 3x plus x, which is plus 4x. Then I'm going to have 1 minus the 4, which is going to give me minus 3. So if I now integrate this and evaluate it between the limits, I'm going to get exactly the same thing. And hopefully you can see the connection right here. So what I can say then is the area is going to be equal to minus 1/3 x cubed plus 2x squared. That's just the integral of 4x minus 3x. And we're integrating now from 1 to 3. So let's go ahead and just evaluate that, and let's get some space down here. The area is going to be now, and then we're going to have now minus, and that's going to be minus 9, so let's put in minus 9. Then we're going to get, so subbing in 3, then we're going to get 18 plus 18, then we're going to get now minus 9 again, so minus 9, and then subtracting away from that, evaluating 1, which is minus 1/3 plus 2 minus 3. So if we look at that one, that first bracket is going to cancel out, and the area is given to be now 0 minus the quantity minus 1/3 plus 2 minus 3. Okay, I'm being a bit lazy. Let's put that through a calculator, and hopefully it's going to be 4/3. So let's go ahead and do that. So we want now minus, then we've got now minus 1/3. So let's do minus 1/3 plus now the 2. And then minus 3. Or I could have just done minus 1. And that's going to give us that 4/3. Okay, so you can see it does exactly the same. So from my opening line, integration is seen as a tool for summation. And we've done exactly that right there. So that's two different ways you can do it. Now, the second method isn't always applicable. So it's often deciding which you're going to do. But we might have, for example, let's say we got some curve. And let's just draw a curve. We might have some quadratic. So we might have some quadratic, and it'll look like that. Okay, so that's a negative parabola. We might have some line, some linear function, and it might do something like that. So what we might be asked to do is find the area now trapped here. Now we can see that we've got these 2 points of intersection. If that's not the case, we need to reconsider what we're doing. But if we've got this and we've got this, I've got two choices to find this area right now. So say I wanted this area. My first choice would be to find the area of this triangle. So whatever the points of intersection are, let's just consider these points of intersection. There's going to be one just here. Let's just say that this was going to be, let's say this was 2. Let's say that this was 2 and this was going to be 6. Now let's say that this gave me a value just here. Let's say that this was 2, 8. Okay, these are just guesses. What you've got then is the triangle, which is going to be an 8 by 4. So we could go ahead and find the triangle. The triangle 8 by 4 divided by 2 is 16. Then what we could do now is From this, we could take the integral of now the curve. So let's say the curve had some function of x, and we would just take this now from 2 to 6. So we'd say the integral of y dx between 2 and 6 minus now the area of the triangle, which is going to give us the 16, and that would give us this trapped area, because now we've got a triangle under here. So find the area of that, find the area trapped under the curve between the 2 points of intersection, and then we'll take it away. So that's doing it with the triangle. The alternative is to take the line away from the curve, then integrate and evaluate between the points of intersection. As stated, there'll be times when it's more beneficial to find the area of the rectangle, the triangle, whatever it is, the trapezium, and subtract away. But sometimes you can just simply subtract one from the other. In a later video, we'll look at a range of different examples of where one would be a better choice than the other in terms of cutting down, certainly the legwork, and also just considering some certain scenarios. So there we go, that's a brief introduction to finding the area bounded by a curve and the x-axis, or if you like, bounded by the curve and the y-axis if we wanted. We would just simply have horizontal strips rather than vertical strips. That should give you enough information and skills to work through those three different examples. One where we have a straightforward integral between 2 points where the curve is all above the x-axis. One where we have, for example, a cubic function or quadratic function where we've got a part of the curve above the x-axis, part below, that you're going to take the modulus, and also then looking at using these examples when we have a curve above a line or a line above a curve. As stated, sometimes you might get a curve above a curve, but it's becoming less and less frequent. So next video we will do some more challenging examples.